So here we're going to talk about integration using the natural logarithm. Now, we need to recall that we know that the derivative of natural log of a quantity, the derivative with respect to x of natural log of some quantity, is 1 over that quantity times the derivative of that quantity. And so let's do some specific cases. The derivative with respect to x of natural log of, let's say, x to the third plus 2x, the derivative of that expression is 1 over that expression times the derivative of that expression. We can either take it from here or here, and that in this case would be 3x squared plus 2. Now, if you just leave it like this, that's fine. But one thing we could do is we could simplify this. Remember, this is 1 over this expression, and this is an expression over 1. So top times top, bottom times bottom. What we could do is rewrite this in this form. And so this is very often done. And what we have now is a fractional expression. And since we know the derivative of this expression is that fraction, we also know, because of the fundamental theorem, that the antiderivative or an antiderivative of this expression is that original expression of the natural logarithm. So what we're going to do is we're going to take a look at expressions of this type, fractions of this type, and use our knowledge of the natural log function to be able to get from this function to finding its antiderivative. So that if we want to find the antiderivative of this expression. Now, what happens is these tend to fall into certain patterns. There are certain rules or practices that you can employ to help you get the correct result for this antiderivative. One thing to bear in mind is there is no quotient rule for integrals. There is no quotient rule for integrals. If you try to make up some sort of a quotient rule for integrals, you're off base. It doesn't work. There is no quotient rule. There's no product rule. There's no chain rule. Not like derivatives. These are antiderivatives. There is no quotient rule. One possibility to look for when you're dealing with fractions is to look for the natural log form. An indicator that this might be a natural log form is to investigate the degrees. Notice that the degree of the denominator, in this case 3, is 1 greater than the degree of the numerator. That's an indicator that might let you know that this procedure this antiderivative is going to be found using the natural log rule. It's not set in concrete, but that's an indication. And so what we're going to do is this. We're going to do a u substitution. Let u equal, and a common occurrence for this sort of expression, when you have the fraction involving polynomials, a common attempt, or one thing you can try, is to let u equal the denominator. And then we need to find the differential. So we've accounted for this. This is now 1 over u. We're going to translate everything into the u language. But now we need to find the differential. The derivative of x to the third is 3x to the second plus the derivative of 2x is 2. And that's times the derivative, that's the derivative with respect to x. And notice that is exactly what we have left over. So how do you say x to the third plus 2x in the u language? You say that as u. And so let me erase this. And so if we substitute, instead of this expression, we have u in the denominator. And instead of 3x squared plus 2 times dx, that translates as simply dx. Now remember, if the numerator is vacant, you insert a 1. If the numerator is vacant, you insert a 1. And so what we have then is, this is the basic form. This is the basic form for the antiderivative of 1 over u. Remember, that antiderivative is the natural log. We must have absolute value. Natural log absolute value of u. And so that's what we have here. So if you do this correctly, if it works out correctly, then what you'll generate is this basic form. This is the natural log of absolute u. And this is the answer in the u language. And just like on all u substitutions, we need to translate back to the original x language, or that's what we're going to do here. And so we go to the let statement. We let u equal x to the third plus 2x. And so this is natural log absolute x to the third plus 2x, absolute, plus the constant, and we're out. And so this sort of a process, this sort of a procedure is going to happen over and over and over again. Especially watch for if the denominator degree is 1 greater than the numerator degree. If this is degree 4, this is degree 3, this is a technique you might want to employ. If this is degree 5, this is degree 4. This is a technique that might well work. So watch for that, and we'll do a couple more examples of that here. All right, so what do I have? I have my little example here. I have the antiderivative x to the second over 5 minus x to the third dx. Notice degree of the numerator is 2, degree of the denominator is 3. This looks like it might fall to our let u equal the entire denominator, not just this piece, the entire denominator. The derivative of both sides, the derivative of 5 is 0. That vanishes. The derivative here is negative 3x squared dx. I don't want negative 3x squared dx. I just want x squared dx, right? So I need to multiply by negative 1/2. So this implies that negative 1/3. Negative 1/3 du is equal to x squared dx, and the substitution is now exact. Everything is accounted for, so x squared dx is negative 1/3 du, and 5 minus x cubed is u, but that's in the denominator. If the numerator is vacant, insert a 1. And then this follows the natural log pattern. The constant multiplier multiplies along, absolute of natural log absolute of u, and then go back to the original variable from the let statement. So this is negative 1/3 natural log of absolute 5 minus x cubed plus the constant, and we're out. You could rewrite that in several different ways. We're just going to leave it like that. So integration using the natural log is relatively straightforward. Now, there are a few variations on this theme. Notice here we had degree of denominator is 1 greater than the degree of the numerator. Now, something like this might arise. We have the antiderivative of, let's say, x to the 4th minus 2 over x. If the denominator is a single term, then what? Notice this degree is not 1 greater. This is not 5 and 4. This denominator degree is less. If the denominator is a single term, very often what works is split the numerator. And so I'm going to rewrite and split the numerator. So x to the 4th over x minus 2 over x. And very often you don't necessarily need to, but you could split this into 2 separate integrals. In this case, it's not, I'll go ahead and we'll just write this as x to the 4th over x is x to the 3rd minus this is 2 over x. And if you prefer, you could write this as 2 times 1 over x. So the antiderivative of x to the 3rd is x to the 4th over 4. And then the antiderivative of 1 over x is natural log absolute x. What about the 2? The 2 is a constant multiplier. It just multiplies along. What you may do, if this is confusing, what you may do, if you wish, is split this into two integrals. So I just took this constant multiplier and threw it out front here. And then each of these, this follows the power rule, this is the natural log rule. One small detail, if you do this, then when you write this as x to the fourth over 4, if you add this constant, think of this as being constant number 1 minus 2 times natural log absolute x, and then this is plus constant number 2. And then what I'm going to do is rewrite this, and I'm going to say constant number 1 plus constant number 2. If you add together two constants, you simply get another constant. So this is constant sub 1, this is constant sub 2, this is just constant. If you want to, you can put sub 3, but you don't need to. So by hook or by crook, if you need to, split into two separate integrals. If you don't need to, you can do each one as you go. But that's the result. Very often, if the denominator is a single term, a monomial, if the denominator is a single term, then split the numerator as a way. And then notice we actually did end up still using the natural log rule in this case. So that's a technique to watch for. All right, so let's play a few more of these. I have x squared minus 2x. And that is over x to the third minus 3x squared. Notice degree here is 3, degree here is 2. And so my leadoff pitch is going to be let u equal this denominator. And if this works, we're going to be fine. And I think it actually is going to work. The derivative with respect to u, the derivative here is 3x to the second minus 6x dx. I don't want 3x to the second minus 6x. But is it clear what I can do here? I can factor out this 3. If you factor out this 3, that is going to leave me with the piece. See, this is the leftover bit for which I need to account. I need to account for this piece, and then factoring out this 3 is going to get the job done. So du is 3 times x squared minus 2x dx, and that actually is what I want to have. We need to get rid of this 3 multiplier, and we've done this several times by now. This is now multiply both sides by 1/3. And the substitution is now exact. And so x to the third minus 3x squared, that gets replaced with u. All the rest of this gets replaced with 1/3 du. And so this is equal to 1/3 du. And since there's nothing left in the numerator, it's 1 over u. And then that follows the same familiar path. So very often, the difficult part is arranging for everything, getting all your ducks in a row. But the actual calculus portion, well, there is some calculus with this derivative, but the actual antiderivative is straightforward. This is just a natural log rule. This is natural log absolute u plus c. And then copy paste the value from the let statement, x to the third minus 3x squared. And it's all over but the shouting. So I think if you practice this a few times and several goes, you're going to be in good shape. In the assignment I'll have you do, there are a couple where you actually do need to split the numerator. There is one little special item here I did want to take a look at. This is 2x squared plus 7x minus 3. Over 2x squared minus 7x minus 3 over x minus 2. We want the antiderivative of that expression. Now notice the degree of the denominator is less than the degree of the numerator, but we're not going to split the numerator because we don't have a single term. We have a binomial, 2 terms. If the degree of the numerator is larger than degree of the denominator, you go off to the side. There is nothing for it. Go off to the side. And see how much of your basic algebra you remember. Do this long division. If you don't know this long division, you need to go online, find a little video for long division, and remember your glory days from basic algebra. What times x gives you 2x squared? That's 2x. So multiply 2x squared minus 4x. Change the signs and add. This becomes 11x minus 3. The multiplier is 11. 11x minus 22. The rule is change the signs and add. This is plus 19. And so once you get this divided out, then you may rewrite. Let's check my work here. This is 2x squared minus 4x. Change the signs and add, becomes plus. That's 11. That's 11. Bring down the 3. That's negative 11. That's negative 22 becomes positive 22. I believe that's correct. So we're going to rewrite this as the antiderivative of 2x plus 11 plus 19 over x minus 2. And what I would do is split this into two integrals. Split this into the first two together, 2x plus 11, and then split this into this constant multiplier comes out front. Power rule, use substitution if you want to do this to find the natural log rule. So here we're going to let u equal x minus 2, du is equal to dx. The substitution is exact. So this becomes the antiderivative of 2x plus 11 dx. And this becomes integral of 1 over u du. Antiderivative, that's 2x squared over 2 plus reattach the variable. And then this is 19 natural log absolute u. And then if we want to clean that up a little bit as we go, I need to replace u with the x minus 2. So that's x squared plus 11x plus 19 absolute x minus 2. And you're out. Now that's a lot of mess, but this is the key. This is remembering your basic algebra to know how to do the long division so you know how to rewrite this. Once you rewrite this, that antiderivative is easy, that antiderivative is easy, and that antiderivative is easy because it's a basic let u equal the denominator. And that becomes the natural log rule. So anytime you have the degree of the numerator is greater than the degree of the denominator, that's a technique you can employ. All right, so let me do one more of the natural log rule and we'll call that a day. I'm going to say let's see here. We have I have the antiderivative of cosecant squared t over cotangent t dt. We could throw a lot of trigonometry at this, but what we can do here is let u equal cotangent. And what's the what's the derivative of cotangent? Derivative of cotangent is negative cosecant squared, which is almost exactly what we want it to be. All we need to do is get rid of this negative sign, and we know how to do that. Multiply both sides of this equation by -1. dt, not dx, dt. And the substitution is exact. And so this becomes negative antiderivative. This is 1 over u. This is du. So this is negative natural log absolute u plus the constant, which is negative natural log absolute cotangent. And you could rewrite that a few different ways, but for our purposes, that is sufficient. So whenever you have fractions, the natural log tool is one very standard tool to find antiderivatives.